Hello everyone, good evening. Welcome to week 8 live interactive session of Advanced Computer Networks course. My name is Ranjita. I'm a PhD scholar from Department of CSE IIT Hyderabad. So in the week 8 lecture, basically the topic covered was on programmable network. So the concept of P4 and PISA architecture was covered, and why the SDN OpenFlow was not sufficient and what led to the rise of P4 and PISA architecture, and with such a programmable or reconfigurable hardware, what is it that we achieve in the networking domain. So that would be the outline of the course. We'll get started. So the major idea is, okay. So the main idea is in the week 8, the major topic covered was basically P4 and PISA architecture. So before directly jumping into P4 or PISA, let's just revisit the concept of SDN and OpenFlow so that we'll be able to appreciate what PISA and P4 brings into the networking world. So I'll just quickly touch upon the SDN concept, the concept of generalized forwarding that SDN had, and how OpenFlow helped there, and then we will see what were the shortcomings there and what led to the PISA and P4. Okay, so in SDN basically it is like decoupling the control plane from the data plane. So in the traditional network, we had these switches and routers, which were hardware boxes. So both we had all the software network protocols running here. We call them the control plane. And then we had the match action tables or the routing tables or the L2 source address table, R table. All these tables were also in the hardware box, and we call them as the data plane. So with SDN, what we did was we just removed this control plane outside, and we placed it in a remote centralized location called SDN. And then we had multiple data planes, which basically contain only the data. It had only the match action tables. So there was basically no software component or any the routing. So earlier we have seen in the previous classes that typically these routers learn the routing table information by exchanging protocol specific control packets, and then the routing table gets built, and then these are the then of the various routing entries, the best routes gets installed in the forwarding plane or the data plane. And when a packet comes, the packet touches only the data plane. It doesn't touch the control plane. So control plane does not process the data plane. They process the protocol packets, build the routing table entries, and install the entries. And using these entries, when packets comes, it gets process. So that is how control plane and data plane operate. And with SDN, we brought this control plane outside in a central location, and SDN will, the SDN controller will communicate with all the data planes. So whatever routing table entries needs to be there in each of the data plane, the SDN will install them, and this API using which they communicate is there is an open flow standard. using open flow standard. The controller and the data plane communicate, and they will be the rules will be updated and packets will be processed accordingly. So one major aspect of SDN or advantage of SDN that we cited at that time was, since the control plane or the software component have been taken out, these are all kind of commodity hardware which will have the generalized forwarding table structure. And then since the API is also standard, the cost of these data plane devices came down drastically. And in the traditional setup, when we had the black boxes, like both the control and the data plane in it, we had separate L2 switches, and we had separate boxes for routers which used to route the packet. This is switch, so this will read only up to the L2 header. So only if you see in the physical in the OSI layer or IP TCP IP layer, physical layer, we have the link layer, we have the IP layer, and we have the TCP, and we have the application layer. So typically in a network device which is a switch, it will be processing packets only up to these two headers of the packets will be looked up, and accordingly the forwarding will be done. Whereas in routers, these three headers will be looked up and the forwarding will be done. Okay, and ACL and all, I mean firewalls and all will look into the layer 4 header also. Okay, so a firewall, we used to be another device, hardware device, a NAT box used to be another device. So all these were different boxes for different functionality. So basically, a NAT box will not be typically doing a routing or a firewall job in that way. So because it is all closed, it's custom built. This is how the NAT has to operate. So the hardware is optimized for it, and accordingly the software is also written there. So for various functionalities, various middle boxes, we had to have different boxes. But with SDN, we brought in the concept of generalized forwarding, wherein this dumb data plane, which does not have any software running it, this particular data plane uh, can act as an L2 switch, can act as an L3 router, can act as a firewall, can also act as a NAT device. So to achieve this, we have the concept of generalized forwarding, wherein all this hardware box will support a set of match action units. So all these hardwares will be supporting something called as a match action unit. So typically the match will be done on packet headers, and based on the match, certain actions will be taken on the packet. It could be forward, drop, send to controller, etc., etc. Various actions will be taken. So that is so with this. So since we are bringing in this generalized forwarding concept, like the data plane should be able to act as an L2 switch or an L3 switch or a firewall or a NAT device. It should be able to process a lot of headers, wherein in the earlier scenario, we saw that an L2 switch needs to process only these two headers. An L3 router needs to process only these three headers. Those devices will look the rest of the packet as a payload only. Whereas for in generalized forwarding, all because we don't know, like, am I going to use this hardware as a switch? Am I going to use it as a router? We don't know, right? So to have it generic, this will supports a lot of protocol headers, such that this can be used as a switch or a router or a firewall or a NAT. So let's just take an example and understand what I mean by this, the generalized forwarding. So typically, yeah, as I said, we will have this match action table. So if I want to achieve a simple destination based forwarding, typically in the generalized match action tables, the header fields supported are typically source MAC, destination MAC, um, Ethernet type, then VLAN ID, VLAN priority, then source IP, destination IP, IP protocol, type of service, then TCP or UDP source port, then destination port. Then we have the action. So we on the match side also ingress port, on which port the packet came. So we have these many, I mean, this is just a simple snippet, these many headers of which this will go to the L2. These are like the L3 part, and this comes the L4. So this is a simplified match fields that a generalized forwarding table will have. Now, if I need to have a rule in the forwarding table such that all the IP datagrams destined to address 51.6.0.8 should be forwarded to output port 6, how the table entry, the forwarding table entry will look like is, all these fields we are not bothered about what the ingress port is, what the source MAC, destination MAC and all. So all of them will be wildcard entries. And the datagrams destination IP is what we are bothered about. So this destination IP field will have 51.6.0.8. Then again IP proto, IP type of service, all this will be star. And the action will be, we need to forward it to port number 6, right? Output port number 6. So we mentioned that here. So this is our generic in a generalized forwarding table. This is how the rule will be. Now suppose if I want to if the condition or the I want to make the data plane act as a firewall, and what we want to do is block all datagrams destined to TCP port 22. Okay, so in this case, we are only bothered about all the packets that are destined to 22, that the action needs to be dropped. So we are not bothered about all these fields, source MAC, destination MAC, it type, VLAN, prior, source IP, destination IP. All these will be star except the destined D port. This destination port alone will be, so everything will be star, and the last field will be 22 and the action will be dropped. This is how the table rule will be. So you can observe that like a lot of the fields are not being used, right? But since we have come up with a generalized forwarding mechanism, this is how the headers are supported by the vendor. So this is what generalized forwarding means. So even though we did we actually did the control plane, we removed the control plane, we decoupled the control plane CP and DP. The DP is still DP capability, or the tables or forwarding match types that the DP support, the data plane support, is still decided by the vendor. Though we have OpenFlow standards, so in OpenFlow 1 standard version 1, I think the number of headers that was asked to support was around 10 or 12 or so. And as the version improved and they started supporting more and more protocols. I think in version 3, the number of protocol header, like this generalized forwarding header that I just showed here, right? This is like how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This shot up to as high as 40 or 40 plus. Okay, so the difficulty here is the data plane is still the hardware is still from the vendor, and if the vendor decides that I am going to support only so and so header fields, like OpenFlow have multiple versions. If the vendor decides that I am going to support OpenFlow 1, only those many header fields will be available for match action. Okay, so vendor decides the match fields. So tomorrow, so if I want a like proprietary protocol or a custom protocol or a new protocol, if I have defined, and if there is a new header which has a new header, then we still need to wait until the vendor provides the support in the hardware. So this dependency with the vendors on the the table that they support, that is still there. It's not taken away. This was one major issue. So even though we did the decoupling, it brought in, it helped in lot other ways, like enhancements or trying out new protocols and testing out new protocols on the switches was still time consuming, because the table was still decided by the vendor itself. Even though we say it's a generalized forwarding, if the box supports only 12 match headers, then only those set of functionality can be achieved using that particular data plane box. If another vendor support, for example, all the 40 fields that OpenFlow 3 specification asks, then all those functionalities will be supported. But if a new custom protocol I want to test, then it will not be possible. We will have to wait until the vendor makes the necessary changes and supply the hardware accordingly. So that was one issue that was still not solved with SDN. So hardware is still the table structure or the match fields are still decided by the vendors. Another issue was like this is a fixed size table, so it was fixed size table. Though we support multiple tables, this T1, T2, T3, all of them were fixed size. For example, as we already saw here that a switch actually needs to look into only these two header, whereas a router needs to look into all the three headers, like IP header and L2 header. A firewall will have to look into the transport, the IP, and the link header. So with a generalized forwarding, we are actually, if I am using this device as a switch, I'm actually still wasting a lot of time, a lot of space in the hardware, because let's assume that we have a simple 12 header match. Okay, so it comprise all the 12 headers that I just mentioned here. The source MAC, destination MAC, VLAN, VLAN prior, Then Ethernet type comes here. Then we have IP source, destination, type of service, protocol, and then we have a destination source port, destination port. Okay, but if I am going to use my data plane, if my data plane is being used as a L2 switch, I actually don't need this information at all. The switch will never be looking into this information and processing it. But since it's a generalized forwarding and the vendor doesn't know like for what purpose this box is going to be used, uh, actually a lot of it doesn't lead to optimized use of the underlying hardware resource as well. Actually, it's a like pro and cons. Like earlier, the same argument was used to tell that okay, because we have a generalized forwarding, the same hardware can be used as any of the device. But now, I mean, this itself becomes a disadvantage that. Uh, if I know ki I'm gonna use the data plane as a layer 2 switch, the rest of these headers are actually getting wasted. So resources not optimally used. So these were the issues that we were having with respect to SDN. Not with respect to SDN. SDN did not solve these problems. So ideally, one should be able to the solution. What we actually want is like we should be able to dictate the kind of table the hardware will support. Okay, we should be able to dictate. So, for example, if I want to use the data plane as a L2 switch, then I should be able to program the device such that we will be using only the necessary headers and only the L2 specific functionality should be achieved. But if I am going to use it as a L3 router, then I should be able to define the match headers accordingly. Here, if I'm going to use my data plane as a L2 switch, then I should be able to define the match header accordingly. Same way for if I'm going to use it as a NAT, I should be able to define the match headers based on the on how I am going to use that device. So this is what we are going to look at. So this whole concept is called as so these issues that we just discussed that SDN could not solve is being solved by this new concept of programmable hardware devices. Programmable switches. So, something called protocol independent pizza architecture came in, which is protocol independent switch architecture. Architecture came in. Okay. So what this by protocol independence, what we mean that uh, the box will come, but the capability or the different match types that the box can support will be dictated uh, by the using programs. Okay, so irrespective of whether I am going to use it as an L2 switch or an L3 switch or a NAT device, this architecture will allow the user to program the box accordingly. So typically, that's the reason why it is called protocol independent. So underlying hardware will be the same. The hardware layout is going to be the same, and based on what network protocol we want to run on it, we will be able to run it accordingly. So there is this language which help us language that help us a language that help us program this hardware, and that language is called P4. So the P4 so this is for programming protocol independent packet processing. So this is 1P, second P, third P, and fourth P. So this is the language. Okay. So so to allow the network box to be programmable, the way the operator wants to use it, whether the operator wants to use it as an L2 switch or an L3 switch or a firewall or a NAT or whatever manner, we should be able to program the hardware such that the necessary functionality is achieved. So this takes away any kind of dictatorship from the vendor side. So this PISA architecture on this switches which follow the PISA architecture, we will be able to program and run the protocols the way that the operator wishes to. So tomorrow, or I want to have a new protocol, a custom protocol, which is different from IP or any existing protocol. I want to test something, or I have designed a new protocol and I want to test on it with a custom header, and all the protocol have some header fields and all that. Then using this P4 language, I will be able to program my PISA switch, and I'll be able to run my custom protocol and test it. So any kind of custom protocols. So with this, we will be able to achieve. So this brings in the this takes away the complete vendor dependency that earlier we had with the SDN data planes. Okay. So is this clear? Any doubts? Okay. I'm audible,
Yes,
right? I
yes,
think.
a custom protocol, ma'am.
Sorry.
Custom protocol.
Yeah. Custom
Ma'am,
protocol. Huh.
ma'am, I want to previously recorded video, ma'am. How to find?
No, no.
Could you teach us, ma'am?
Come again. I didn't hear you.
Ma'am, previous recorded video.
Okay, previous recorded video, it is available in the portal, right? I think so. You can go here,
Oh,
problem solving session. So,
okay.
you go here, it will open up the videos. So you can click to and click and watch them.
Okay. Ma'am, one question, ma'am. Suppose
Yeah.
IP camera is not working and suddenly their IP address is becoming 1111. That what is the reason, ma'am?
Come again. What is not working?
Suppose IP camera is not working, and when I change their IP address, then IP become 111,
One,
6
one,
time 1.
one. I mean, I'm not actually getting the context of the. I mean, I
Oh,
think
like,
I understood that you were facing some issue with some configuration, but
yes, ma'am. Ma'am,
I'm not
no,
sure
ma'am,
I could.
already
Yeah.
configured, but
Huh.
IP camera is one problem. They are not getting online. I multiple times ping, but sometimes they are IP address becoming 4 time, 6 time once, but not online.
6 times 1. I'm not able
What
to.
is the reason, ma'am?
Yeah. No, I don't know. I'm not able to get the context actually without understanding the topology and the setup, what you
Actually,
configured,
working in
how
a ring
you
topology, ma'am.
configured.
Actually, I'm working in a ring topology. I multiple times edit their IP, but sometimes their IP becoming 6 time once, and camera is on showing online, but actually their camera is offline.
No, upfront, I'm not able to answer what could be the reason. But I think it's not related to the current topic that we are
Yes, ma'am. But ma'am,
discussing.
I'm facing some problems, so I want to solution, ma'am. So asking question.
Yeah, I understand. Can we take it after this session? I mean, I can
O-
just finish this in the flow and then take it.
Okay, ma'am. Okay.
ഓഫീസ് ആരോ വരുന്നുണ്ട് എന്ന് പറഞ്ഞില്ലേ ഓഫീസ് ആരോ വരുന്നുണ്ടോ ഓഫീസിലുണ്ട് ചേട്ടൻ വരുന്നുണ്ടോ
Ma'am, what is custom protocol, ma'am?
Yeah, so custom protocol is nothing but any new protocol that you want to design or test or anything that is not standard. Like you're working on some research problem and maybe you come up with some protocol with which you want to explore certain aspects. So we call those protocols custom protocol, which is not a standard. It's like for your own research and your own
Yes, ma'am.
problem
Yes,
solving.
yes.
We come up
Yes.
with some custom
Particular
made
use, ma'am. Okay.
things.
Noted.
Yeah, something very custom made by us ourselves. And the beauty of programmable hardware is that we can test it on the hardware because
Okay.
it is programmable. The switches that support pizza architecture, we can program it because it's completely the box as such doesn't do anything. It doesn't know anything about the uh, protocol. So basically, on a switch that follows the pizza architecture, a switch that follows pizza architecture, you have not loaded anything. You send a data packet here. The switch doesn't know how to process it. It doesn't understand Ethernet header. It doesn't understand even the standard protocol until we configure and tell the switch key. Okay, this packet will have Ethernet header. It will have IP header. It will have my custom header. Then you first retrieve the Ethernet header, you take the IP form, then you take my header, and then you process it in XYZ form. That is how we actually instruct the hardware to do the processing, like how we normally write a C program. Like we write our logic there and then run it, right? On the
Okay.
x86 CPU. Same way, we write our logic and then we get it run on the underlying networking box. So how this is achieved? So pizza architecture basically comprise of three components, we can say. So first we will have a parser. Then we have something called match action units. And then we have a deparser. So in the parser part, we will program and tell like how parse the packet, like if I am writing a L2 switch program, then in the parser will take care of parsing the layer 2 header, the source MAC, the destination MAC, the layer 2 header, L2 header will be parsed. If I am writing a router program, then L2 header and L3 header will be parsed. So we will write accordingly, and the parser will take care of parsing the packet. Parsing the packet means that looking at the protocol fields one by one and retrieving the values from it. That's what basically parsing means. And in the match action unit, the logic of how we want the packet to be processed is written. Typically, it is written as a match action table. So, if it is a routing functionality, if we want the packet to go, like if the destination address is 10.10.10.10, forward it to port number 1. So these kind of information we will provide in the match action unit. We will define the tables, will define the table structure, basically how many, what is the key of the table, on what protocol field the lookup is done, and then what are the other columns in the table. All those details will be defined basically in the match action unit. Then once the whole processing is done, we need to send the packet out. So that time we again club all the so during in the match action unit, during the processing of the packet, certain headers gets modified. So we need to put all those headers in order and then send the packet out. So this is how a typical pizza architecture looks like. So the just a minute. Right. Yeah. So this is how the typical pizza architecture looks like. Okay. So we bring in yeah, switching logic. Okay. Right. Now let's maybe take a look at and how we typically program this using P4 program. How do we write the program, and how do we get it run, and how our functionality is achieved. Okay, so what we do is we will, so basically we have to program the pizza chip using P4 language. Yeah. So what we will tell is, we will first tell the switch how to process packets. Tell the switch what packets needs to be recognized. Then what all should be the tables. Okay, so this is what we will do. We will write the logic and with all these instructions. Then the program that we write in P4 will be compiled. Then it will be run on the pizza switch. Okay. Yeah, now let's slowly go look at what this P4 program is. So this much is clear, right? Like we have a hardware box which doesn't know anything. So it first it will have a parser unit, a match action unit, and a departure unit. As per the PISA architecture, we will have a hardware box. Then we program that hardware box. Basically, we tell the box how to process the packet, what packets should be processed, what all are the tables that we need. We tell all this information using the P4 language. Then we compile. So basically, we write the program in P4 language, we compile the program, and then the binary is run on the switch. So once we run this on the switch, whatever functionality we wanted, if it was layer 2 switching, if it was layer 3 routing or firewall or any custom functionality that we wanted, that will be attained using this
Ma'am,
program.
ma'am,
Yeah.
P4 programming and PISA switch. Tell me something, ma'am, about the
Yeah, that's what.
P4 compile
Yeah, before
on PISA
first
switch.
we write the program.
Hmm.
We write the program in P4 language. It's a language like C, Java, Python. It's a language,
Hmm.
okay?
Hmm.
So there is a specification given for the language and all. We have to write it based on the syntax and
Ma'am,
semantics
this
of
is
the
my first class,
language.
ma'am.
Huh?
This is my first class attending first class.
Okay, okay, okay. I will show an example of a P4 program, okay?
Okay, okay.
Yeah, we will be seeing that. Okay.
Ma'am,
So,
you have to provide me recorded video, ma'am.
yeah, it will be uploaded in that Excel sheet which I showed, right?
Okay, okay.
So this is this. Okay. Oh, you wouldn't have seen because I was sharing a different screen. But once I'm done with this handwritten thing, I will show you where you can go and check in the Swayam portal.
Okay,
These links are actually updated in an Excel sheet. I'll show it in case if I don't show it, remind me. Okay.
okay, okay.
I'll show it
Ma'am,
before.
try to find out, ma'am, but because, ma'am, due to rotation shift, I cannot attend classes, ma'am. I have no practical knowledge, but not a theoretical knowledge, ma'am. So theoretical knowledge is very important.
Yeah. Yeah, I'll show it probably towards the end of the session. So in case if I miss, just
Complete, ma'am. If
remind me.
complete PDF notes, then we provide you, ma'am. Complete PDF notes.
Everything we are providing. Okay, I'll right away show you. Just hold on. I'll just share the screen and show you. Okay.
Okay, ma'am. Okay.
So you are able to see the portal, Swayam portal. Are you able to see my screen?
Ah, yes, ma'am.
So you can see the portal, right? So go here. You can see this problem solving session.
Problem solving. Yes.
So yeah, go here, then click here.
Problem solving session. Okay.
Then that will take you to a Excel sheet. So in the Excel sheet, both the TAs, we have uploaded the recorded video in YouTube and the YouTube link is given here. So two TAs are
Okay. Okay.
taking the session. So both of us upload it here. And this is the drive link where all the materials you will be able to see. So if you go here, all the handwritten notes, week 1, week 2, week 3, week 5, all are there. So you just have to go to this place, okay? Go here, problem solving session recording. Is it clear?
Ah, yes, ma'am.
Okay.
Suppose any problems come up within a week study, and how to solve, ma'am? I solve
Yeah,
problems from Google, ma'am.
I'm not able to hear. There is some noise coming in the background. You can type in. I'm not able to actually hear properly. I'm sorry.
Yes, ma'am. Actually, I am working in a data center also, ma'am. My total work is storage is SAN storage.
Mhm. Okay. Okay, so we'll continue the class. We'll look at P4 program and understand how we can
Yes,
program
yes,
the hardware.
yes.
Yeah. My screen is visible, right?
Yes, ma'am.
Yeah, yeah. Yeah. So let's take an example of a simple IP forwarding functionality. And then see how we using P4, how do we write the P4 program to achieve this particular functionality. Okay. So let's assume that we have some hosts connected over a LAN. Here there is a router, here there is another router and another router. Which again the hosts are connected and the hosts are in the network 6.7.24.0 and 1.2.3.0.24. Okay. So the requirement is the host from this particular site should be packets should go and reach here, and the packets from these hosts should go in this direction. Okay. So in this router, we are trying to do the P4 program and deploy the program here. So what we need basically for these hosts to exchange the packet is we need when the destination IP is sorry we need to forward it to this direction, and when the destination IP is we need to forward it to this direction. Let's assume this is port number 1. But okay, so now so basically, what are the function to do an IP forwarding? As the simple things that happen when typically when a packet forwarding happens, we basically do a lookup in the forwarding table. Then main then we update the destination MAC. We decrement the TTL and then we forward the packet. This is basically what each IP router normally does. right? So we know that a P4 program comprises of a parser, we have match action and deparser. So since we are trying to do a IP forwarding, we have to basically look at the IP header, right? For an L3 router, we should be looking at the layer 2 and layer 3 header. So the parser sorry. Programmer have to declare the headers that should be recognized. Okay, so what are the headers that should be as I told here? Yeah, tell the switch what packets to be recognized, how to process the packet, and what all tables to keep. So we need to first tell in the parser, we need to tell that layer 2 header has to be looked at, must be parsed, and L3 header must be parsed. So I hope you all know the format of L2 and L3 header. So basically, then L2 header basically comprise of source MAC, may not be in the same order, destination MAC, then Ethernet type, then VLAN type and priority. Then in IP header, yeah, there are a lot of fields. Basically, I don't remember all of them. So major thing that will be of interest is first IP source IP and destination IP. Okay, but the parser we have to parse the whole packet. Okay, so once once we tell okay we are interested in these two headers of the packet, then we have to tell using match action tables, we have to tell how to process it, how to process the packet. So this how to process the packet is uh, what is happening here. So first we will do a lookup of the forwarding table, then we have to do the update the destination MAC, then decrement the TTL and forward it to the outgoing port. So these comes under the how to process the packet. So typically we achieve this using match action pipeline. So forwarding table is nothing but a match table. So we will match the packet on the destination IP. Then based on the match result, whether it is a match or a hit or a miss. If it is a match, we normally call it as a hit. If it is a if no entry in the forwarding table matches, we call it as a miss. So based on the match, we define actions. And the action here will be first to update the destination MAC, then decrement the TTL. Okay, so this will fall under the actions parameter. Now once that is done, we have our deparser. So here we are actually updating the packet header values, right? So deparser will form the final packet that needs to be sent to the what to say, next hop router. So deparser, in the deparser section, we will declare how the output packet should be. Okay. So these are the major three components. Now let's start with the P4 program. So our switch or IP forwarding router, we can call it. It will comprise of, as I told you, we will have a parser. Then we will have a ingress control block where the match action pipeline will be there. Then we will have an egress control block. We will have a deparser and that. So these are the main functions that we will have in the program. So inside the parser, we will it will be typically we will have a the program structure will be like initially we will have some headers like in C we include stdio and all that. Here we have some headers specific to P4. We will include all those headers. Then we do all the constant declarations, all the header declarations, constants header, like we are going to read IP and Ethernet header. So we need to declare those two header structure here. Then the parser will come. Then we will have the control, my ingress, which this ingress will contain match, action, apply and all that. And then we will have deparser. So typically a structure of the packet, I mean structure of the program. So here all the declarations will be there. Parser takes care of reading the packet header contents, parsing the packet header. The ingress, we will have the control flow. Control flow to modify the packet. And then this will assemble the modified packet and send it out. So now let's see how exactly a parser works. Parser is typically state machine. Which it is used to map the packets into the headers and metadata. Okay. So for example, we will have different headers, right? So we have seen a packet will have this is the L2 header, this is the L3 header, maybe this is L4 and then payload. Okay, so by parsing, what we do is, so we would have already declared Ethernet header, IP dot header in the program. This is L4 dot header. Okay, so we need to copy these contents to this header, copy these contents to this header, copy the content from the packet to this header. Then we do the processing, and then after the processing, these content of these headers that we read and we processed it, right? It would have modified. Then we again put them back. That is what deparser does. So this header, Ethernet header, say whatever is there will go to the L2. And whatever is here will go to L3. Whatever is here will go to L4. Then payload will not be touched. Payload will be as such. Then this packet will be sent out. So in the parser, we will copy what the packet fields from here, here, here. I mean, how we are defining accordingly, we will copy. For example, if the Ethernet MAC address was ABC and destination was so after the parsing, what will happen is if I have declared an Ethernet header like structure Ethernet, I will have source map, destination map, then etc. Based on the header format, we actually need to define the structure properly. So after the parser, what will happen is this is the structure Ethernet ETH header. This is the name of the structure. Okay. So ETH header dot source mac will become this value. Then okay, so this is what we mean by parsing. So we first define the packet header structures. Then in the parser code, we will tell what all we wish to read from the packet. And then once we tell that, at the end of the parsing, these whatever content of from the packet will be accordingly copied to the necessary structure. So, for example, let's see a proper example so that it becomes clear. So it's we normally define it like there will it's a state start. This is the syntax, okay, in the language syntax. Transition parse Ethernet. Now we will write parse Ethernet. State parse Ethernet. So we extract packet dot extract dot extractor header dot Ethernet. So this depends on how we have this naming depends on the how we have defined the structure name in the program. So here I have defined saying it header, right? So it will be it header. So this from the packet, the all the content which is equivalent to this hit header will be copied. Based on that structure offsets, all the elements will be copied. Now, after this Ethernet header, we need to parse the IP header also. So we move from one state to another state using the transition. Select statement header dot with header dot ether type. If it is 0x800, we will parse IPv4. This is the Ethernet type, and for IP packet, Ethernet type will have the hex value 0x800. Okay, so we do that. Then in the state parse we are going here, right? State, we declare how to parse the IPv4. So here we extract packet dot extract dot header dot IPv4, and then dot protocol. So based on the protocol, if I want to process TCP packet in certain way and UDP in certain way, we are going to parse that. TCP and so we will not see this TCP UDP thing because we are just simply going to do a IP based forwarding, right? So typically, so this particular parser which I just mentioned, so this is how the state transition is. So it starting state. There is a parse Ethernet. Then after that, we go to parse IPv4. Now from IPv4, I can go to either parse TCP or parse UDP. And then after all this state, we will have a, once the all the parsing is done, it goes to the accept state. From here we can go, from here we can go, and directly from here also we can go. So this is how we define the parser. So basically, if you can see here, I'm using these terms header.ipv4 and header.ether ETH header. So in the starting of the program, we will define ETH header and also we will define IPv4 header. Okay. We will also define struct IPv4 and this structure, this is like a C program. In C, how we define structure, same way we define the IPv4 header as a structure. Okay. Then we will have another structure called header which comprise of ETH header and IPv4. That's the reason we were accessing it using header dot. Okay, so it's just the syntax how the parser works. Now once the parsing is done, we will have the major part is the match action or the control block where we will have the match action tables. So the logic gets executed there. So after parsing, the packet will enter the control block. Okay, there we will have the actions and tables. So this part is the one that takes care of modifying the packet or what needs to be done with the packet. So that is being done in this part. Okay. Let's see what is how a typical match action looks like. Okay. Yeah. So in a IPv4 forwarding, what we need is we need a simple table. We need a table. Okay. And we will do a lookup to the table with key as destination IP. So we do a lookup with key as the destination IP, and then we need to do certain once the table lookup succeeds, we need to do certain actions on it. So in the control block, we will define this. For the IP, for the simple IPv4 forwarding, we have already seen what are the things that needs to be done. So yeah, so we need to the lookup table. So we will have a table which will be looked up on based on the destination IP as the key, and once it matches, we will do all these are the actions to be performed on the match. Okay, so looking up the forwarding table, and if it is a match, we need to do the following these all the three actions. So let's see how a table is defined, how the actions are defined. So a table is the syntax for a table in P4 languages. So we will mention table, then we will tell what are the key for the table. Then we will also mention the actions. Actions are normally mentioned as short, like in C, we have the concepts of functions, right? C and Python, we make programs modular by splitting small logics into small functions. Actions are nothing but such small functions. We can consider it equivalent to functions in C. Then we will also tell the size of the table, and if there is no match, we have something called default action. So that also we mentioned. So this is our typical skeleton of a table looks like. So in the example IP forwarding scenario, we this will go to table. Key is destination IP. Key is destination IP based longest prefix match. So key equal to header dot IPv4 dot DST address, destination address. And how are we going to match on this particular key? It could be exact match. In general, destination IP addresses are longest prefix match, right? So we mentioned the match type as LPM. So this is the only key. Then what are the actions that we wish to do? We want to forward the packet, or we can also drop the packet. We can drop the packet. Then we mention the size as 1024. We can mention it. Then default action is if there is no match, we wish to drop the packet. Now we have to, so these are the actions. IPv4 forward and drop are the actions. So this is the definition, and this is how we define a table. Now we need to define the action. So when a packet comes, and if there is an entry in the table, lookup will be done, and if it is a hit, the action will be called accordingly. So in the table entry, we will actually mention what action needs to be performed. We'll see an example, then it will be clear. But now we have not actually defined what is the action. We just mentioned the function name only. But what are the things done in that function needs to be again defined. So the action IPv4 forward, what it will do, this IPv4 forward, we will give destination address and egress port. I'll come back to this in a while. So we have to first set these are the standard usage. Standard metadata. This we are telling which output port the packet must be forwarded. Now we do the header updation. Ethernet, Ethernet dot then header dot destination address. This comes from the table actually. Then we decrement the TTL. Sure. Okay, unfortunately, couple of content. Maybe that. So this is the action, the forward action. So what actually happens is whenever we try to do an IP-based IP forwarding, I think you all know the source and destination MAC address actually gets updated. So if this is a router and this is another router, so there is a forwarding from in this direction. So the packet comes here, a lookup is done, and it has to go out, right? So for the packet, when it is going out, the destination MAC should be this MAC. Okay. And the source MAC in the packet becomes the, when this packet came, the destination MAC was here. This one goes into this goes into the destination MAC. Okay, the current packets, so first this will happen. Current packets, so this was one. And okay, let me, this was 1.1.1. And if it is 2.2, so what will happen is when the packet came to, this is R1, R2, R3, when the packet came to R2, the destination MAC was 1.1. Okay. Now when R2 is forwarding it out to R3, then first the source MAC. So when it came here, the source MAC was like 3.3. Okay, this guy's source MAC, R1 source MAC. Okay, the source MAC, when it came at R2, the source MAC is 3:3:3. So now when we are sending it from R2 to R3, we need to actually do the swapping. So we put the destination MAC to the source MAC. So source MAC becomes 1.1.1 and destination MAC is actually the MAC of R3. So it will be 2:2:. Okay. So in this header, so this is what we have done here. We are copying the destination address to the source address. Then what destination address has to be given is actually coming from the table entry. Okay, table row. Then to which port it has to be sent is also coming from the table row. That I'll show you how it is done, and then we decrement the TTL. Okay. So this is what a basic how a basic forwarding happens. Okay. So now so what happens is basically when a packet comes, okay, we do the parsing, then we do a table lookup. So we have defined the table, okay, and unfortunately that is gone, the table syntax and all. So we had defined how the table was the key of the table and all, but in the hardware we need to have entries in the table, right? When we do a lookup, we need to have entry in the table. Okay, so what will happen is there will be an entry in the table which will tell this will be the key, which is 1.2.3.0/24. The other entry will be 5.6.7.0/24 for the example that we were looking at. This is the key, and what action we have to take for this. If a packet destined for 1.2.3.0 comes, what is the action that we need to do? We want to do a IPv4 forward. This action must be called, and when we are calling this action, certain parameters also we have to give. So these are the parameters. When we are calling this action has to be called with destination address and egress spec. That also we mention in the table. Okay, that also we mention in the table. So we will tell that destination MAC has to be, what was the destination MAC has to be? Okay, so I will just write something. And destination port has to be 2. Now if for this one again we will tell that IPv4 forward, we will tell, and we will tell port number 3. Okay, so in the program we have mentioned that how the table has to be, what will be the key of the table, what are the action parameters for the table, and what are the actions. But when a packet comes, what action gets executed is decided by the table entry. In the program, we will only mention the key of the table, what is the match type, what are the actions, possible actions for this table. That is what we will mention, and we will also define all of those actions. But when a packet comes, what action actually gets executed depends on the entry in the table. So these entries are also equally important. Okay, so I think you got some idea how it works. Any doubt here? Any doubt? Okay, I'll continue. Okay. So now we have seen that. So when a packet comes for 1.2.3.0, let's take another example, because in the table we have also defined a drop action, right? So if I get a packet for 10.10.10.0 bar 24, we can equally mention drop as an action. And when I say drop, the packet doesn't get further forwarded. Okay. So this also is an entry in the table, right? So then I will be defining drop action accordingly. So there is no action parameters here. I will just do a mark it for dropping. Okay. So then if a packet comes for 10.10.10.1, so the packet gets dropped. It doesn't get forwarded. So for IPv4 forward, we have seen that we have. Why is it happening? So for IPv, so we have seen here that we are modifying the header values, right? The IPv4 header we modified the TTL value, and on the layer 2 header, in the Ethernet header, we have modified the source and destination MAC address. Now we have these modified value. Now we need to again put these modified value into the packet and then send it across. So the once the control block is done, the deparser will come into picture. So deparser will take care of putting these whatever modified values we have modified. It will emit all these header one by one. So this is the syntax typically: emit Ethernet header, emit IPv4, emit TCP. Then all the whatever we have modified, all those get stitched together. Like as I told, this L2 header, L3 header, and L4 header will be put it back, and the payload will be there. And then this packet will be sent out. So this is how the departure works. Okay. So maybe I can show an example. We just discussed this IPv4 forwarding, right? I can show you an example P4 program, since I have written it in bits and pieces. I'll show you a full program from one of the online P4 tutorial site. In case you want, you can refer to that. Okay. I'll just share my screen once again. Okay, so yeah, so this is a NSG ETH Zurich. This is a college, so they have this P4 learning tutorial. It's their GitHub repo. The screen is visible, right? Are you able to see the GitHub page?
No, ma'am, GitHub not showing.
Yeah, you can see, right? Okay. So this is the program that I just discussed. Where is the IPv4 forwarding? Examples. So this is the P4 program, right? So first, so in any P4 program, these are the major components. As I told, we have the parser. Ideally, when we receive a packet, we should do the verify checksum. Just didn't discuss it. Just to keep it simple. Then the egress part. Then before sending it across, we have to do the checksum computation again, because in the ingress and egress, we would have modified the packet. Then finally, the departure. So this is the order in which all these functions will be called. Okay. So first, if you see here, these are the variable declarations. This is the header file inclusion. So I have told you, right, when we write the program, we have to declare the Ethernet structure. So this is the Ethernet structure declaration. This is if you know C, it will be easy. I mean, it's similar to the C structure declaration. So header Ethernet करके we define the header Ethernet which comprise of destination address, host address and ether type. Same way IPv4 header is also defined. This is exactly like how the IPv4 header looks like. Okay. Because only then this will work, because packets follow the standard header format. So if we are working on the standard packets, we have to follow the syntax accordingly. If we are defining some custom packet, then we have to do the like header declarations accordingly. Okay, so this is so basically we have two headers. One is Ethernet and the other is IPv4. So in this program, we'll be looking at these two headers of the IP packet. So in the parser, if we see here, so we start it, then we first extract the Ethernet header. Then based on the Ethernet type, we go to this IPv4. If it is type IPv4, so this is declared on top here. Type IPv4 is declared as 0x80, 800. Then you go to IPv4. Then here again we extract we are extracting header.ipv4. Header.ipv4 is this one, that is this complete structure we will, so these many bytes we will extract from the packet. Okay. So at the end of the parser, we have extracted both the Ethernet header and the basically we have copied the content of Ethernet header and the IPv4 header into the header into our header structure. Okay, now this is the my ingress part where the actual processing is done. The control block, we call it control block, where the actual processing logic is written. Okay. So in the control block, in C and all, we have this main function, right? From where the actual execution of the program will start. Similarly, inside the control block, there will be an apply block and always the execution starts from here. Okay. So this is the first place where the execution will start in the control block. So first we are checking if this header.ipv4 is valid is true. So if the parser successfully extract the header, this will be valid. If the parser couldn't extract that particular header, or if the parser didn't extract, or we are expecting some packet and we got something else, then this will be invalid. So this check is to ensure that we are processing the expected packet. Okay. Now, if we receive an IPv4 packet, of course, we will extract it and this will be valid. And then we do this IPv4 LPM dot apply. Okay. So IPv4 LPM is the table that we have defined. So when we tell IPv4 LPM dot apply, a lookup to this table will be performed. Okay. A lookup to this table will be performed. Now, if you see the definition of the table, the key is nothing but the destination address. IP destination address. So we will do a lookup into that table using key as destination address and the match type is longest prefix match. And we have declared three different actions. So one is IPv4 forward as we saw, the other is drop and the other is no action. So we'll see what are these actions declared. So for in case of drop, we will be marking it to drop. So the switch will drop it off. Um, and in the IPv4 forward case, we are we swap the source MAC and the destination MAC. Then, as we saw, these parameters, these are called action parameters. Okay. So when we call this IPv4 LPM.apply, what actually happens is there will be table. The IPv4 LPM table is there, and there are entries in the table. Let's assume that there are entries in the table. Okay. So the table lookup actually happens with the destination address. Okay. And if that table lookup is successful, then based on that entry's action, corresponding action will be called. Let's assume that the action was IPv4 forward. Then the logic will come here, and the control will come here, and from the table, actually from the table entry, these parameters will be populated. Okay. So based on the destination address, the Ethernet destination address will be updated, and the outgoing port also will be updated. After that, in my egress, we are not doing anything. This egress processing is majorly for multicast paper, etc. Normally, yeah. Then after that, we do a compute checksum because we have modified the header fields. We need to recompute the checksum, and then the deparser takes care of emitting out the modified packets. So this is our this full P4 program. So you can go to the site, and it's a good tutorial to get started with. They have a VM actually. You can go through them and get started with that. Maybe I will also quickly, is this Oracle VM visible? Okay, that is not visible. Give me a minute. I'll present again. Yeah, is the screen visible? Can someone confirm if this so actually I have the same program which I just showed you in the GitHub. So this is the same program. Okay, so we can just check. So I have been telling you, right? We need to have entry in the table, and based on the table entry, the action will be performed. So it's a responsibility of the controller to update these table entries. So this is where SDN controller will come into picture. Okay. So this is one way of, so this is nothing but I'm populating the table, the IPv4 LPM table. I'm adding an entry. So this is one way we can add the entry to the table. So if I get a packet from 10.0.1.1, I will update the destination MAC and I will forward it to port number 1. If I get a packet from 10.2.2, the action is IPv4 forward, and I will update the destination MAC and forward it to port number 2. And the third rule says that, yeah, if I get a packet from 10.0.3.0, then again I will forward it. The action is IPv4 forward. and the action parameters are this destination MAC and outgoing port 3. Okay, so this is how we add entries to the table. So only if we have entries in the table, actually the forwarding will work. Okay, so otherwise it will be when we call the IPv4 LPM apply, if there are no table entries, it will be a miss. So it will do nothing since okay. So only if we populate the tables with the proper entries, forwarding will happen accordingly. And so this is how we actually do program the switch. So using the P4 program, so using this P4 program that we just saw, we are telling the hardware, like how we are programming the hardware. Okay, we are programming the hardware and telling it how to process the packets. Okay, and this by updating the table entries, based on the table entries, the actual forwarding will happen. Okay, so both are it's important, we tell what packets to forward and what how to process the packet using the P4 program, but table entries needs to be updated by the controller. Only then packets gets processed accordingly. Okay. Is this clear? Any doubt? Okay, so we just have very few questions. From the previous years, this is one question, like how many header match fields are defined by OpenFlow 1.3? So it is 1.3, 40 different match fields are defined. The other question is, which of the following statements is bar are correct about P4 language? P4 is a domain-specific language for programming network device. P4 is primarily used for programming the control plane. P4 is case insensitive, statically typed language and protocol dependent language. Can anybody provide the answer? Just read through and so P4 is a domain-specific language designed for programming network devices. Okay, and it is used for programming. No, it's not used for programming the control plane. It's used for programming the network devices. It's a case insensitive. It is. This is the property of the language. It's statically typed language. It's protocol independent. So A and D is correct here. Last question is, which of the abstractions does P4 support? Protocol independence, target independence. Yeah, so it supports compiler independence. That is the abstraction that P4 is providing. Okay, so we write the program in P4 in the given specification. We can compile it for any of the underlying hardware. For example, the one that I showed is for a behavioral model V1. So it's a software emulated model. There are hardware targets like Tofino chip which do this, which is a P4 switch. So the same will work there also. So the abstraction that before support is the compiler independence. We have only a couple of questions from last year because majority of the questions are repeated this year. So I cannot explain those because it's already there in this week's assignment. Okay. So I think I'm done with this. Mm, any queries, any doubt? Yeah. If there are no more queries or doubts, then we can close the session. Thank you.